Lecture 10, Advanced Dynamics Problems 2, Fluidic Drag Force. When we looked at the fastest vehicles on the surface of the Earth earlier, we were saying that the biggest problem was drag force. Let's look at a real model of drag force. In first year, we would often say that the fluidic drag was negative b times v, so it's sort of proportional to the velocity. This turns out to be reasonable for small objects or very slow speed. For most of the motion and the scales that we're interested in, so anything from the scale of a person or a little remote control plane or a bicycle or a car up to actual airplanes and helicopters, the drag force is better modeled by this equation. So it's a half times the air density, something called the drag coefficient, multiplied by the frontal area, the area that's facing the fluid you're moving through, and the velocity squared. So it goes like velocity squared generally, but it's really a bit more complicated because the drag coefficient, the CD term, can depend in a complicated way on the velocity. Technically speaking, the drag coefficient is a function of the shape of the object, so how streamlined it is, whether it's trying to scoop a lot of air or whether it lets a lot of air past it, and the Reynolds number. Reynolds number is a dimensionless quantity that you're going to learn more about in a fluid mechanics course. For now, basically, we're not really going to need to substitute into Reynolds number that much. I'm just presenting it here so you get a better view of what the big picture of this drag coefficient is. Reynolds number is a dimensionless number. It has no units, and it tells you the relative strength of the inertial forces to the viscous forces, the sort of stickiness of the fluid. The inertial forces go like the density times the length times the velocity, so sort of like a size, a density of the fluid and the speed that we're moving through it at, divided by stickiness of the fluid, the viscosity. Now, just to give you some numbers, air at atmospheric pressure and at around 20 degrees Celsius has a density of about 1.2 kilograms per cubic meter and a dynamic viscosity of 18 E-6 Pascal seconds, whereas water has a density of 1,000 kilograms per cubic meter, about 1,000 times higher, and a dynamic viscosity of 1 E-3, so that's about 50 times higher than the dynamic viscosity of air. Drag coefficients, again, depend on the Reynolds number and the shape. So here's a plot of the drag coefficient for a sphere. The shape would be a sphere, and we're comparing a smooth sphere and a rough sphere versus Reynolds number. You see the drag coefficient scales upwards as we go to very low Reynolds numbers. Below about 100 on this scale, it starts to increase a fair bit. Whereas when we're up in this region between 1,000 and 100,000, the drag coefficient is pretty much constant. It moves around a bit more above that, but doesn't vary kind of inverse to the Reynolds number like it does at very low Reynolds numbers. Let's look at the drag coefficient around 10 to the 4 for many different shapes. So a sphere has a drag coefficient of this, 0.47. Half sphere, about the same. The back side of it being missing doesn't reduce the drag all that much. Cone a little bit higher. Cube a fair bit higher. It's less streamlined than the cone, and so it has about double the drag coefficient from the front. The angled cube a little bit better. Long cylinder about the same as an angled cube. Short cylinder fair bit higher actually due to kind of tailing effects, but the streamlined bodies have much lower drag coefficients. So you can as you can see from this, you can reduce the drag of something by streamlining it by quite a lot. So if you take the same shape, like let's say the long cylinder, and then you decide to, instead of just this rectangle at the front, like this old boxcar shape, you adjust it with streamlining, then you can get a reduction in the drag by about 20 times. That's major fuel savings in terms of cars and vehicles, and so a lot of effort goes into making streamlined shapes. Here's a concept question. Does drag force always oppose motion? Well, not quite. Drag force opposes relative motion between the fluid and the object. If the object is not moving initially, but the fluid is, the fluid can accelerate the object. For example, wind, vacuum cleaners, etc. Example problem, Galileo revisited. Okay, taking the drag coefficient as 0.47 and g this time is 9.81 meters per second squared as a constant, find the terminal free fall velocity of a brass ball in air as a function of its radius. What falls at a faster terminal velocity, an r equals 5 centimeter brass ball or one with r equals 10 centimeters, and by how much? All right, so this is a question about comparing the terminal velocity of two different sized objects. We can get the terminal velocity by setting the drag force equal to the gravity force, where the gravity force is based on the mass. So as we make the ball larger, we increase the mass proportional to the radius cubed, but we increase the area only proportional to the area to the radius squared. So intuitively, you'd expect that a larger object would have a higher terminal velocity because of that scaling. Sure enough, we find that the terminal velocity scales like the square root of r. So the bigger brass ball is going to have a faster terminal velocity. And specifically, we find that the 5 centimeter radius ball falls at a terminal velocity of 141 meters per second, whereas the twice as wide one, and thus 8 times as massive, falls at a rate of about 200 meters per second. Follow-up problem to this is write but don't solve the differential equation of motion and initial conditions of a brass ball of radius r released from rest from a height 0. So this is not just about finding the terminal velocity, it's about finding the entire differential equation of motion. So writing down Newton's second law for this object. Basically you set ma, so m y double dot, since we're just dropping, it only occurs in the y direction. All the motions, all the actions in y direction, so this is a one-dimensional problem. My double dot is the sum of the forces, which would be gravity down, so the weight, and the drag force pointed up. Since we're just dropping it, then it's always going to have a velocity that's downward. So we know right away which direction the drag force is going to be. It's going to be pointing up. And we can write half rho, where rho here is the air density, CdA y dot squared. And we also need our initial conditions, which second order differential equation will need two initial conditions. The initial height is 0, and we are told that it's released, which tells us the initial velocity was also 0. Skydiving. Estimate the terminal velocity of a skydiver before they deploy their parachute, taking their mass as 75 kilos and their area facing the fluid as 40 by 20 centimeters with a drag coefficient of 0.82. Assume this is in air, so density of air is 1.2 kilograms per cubic meter. We're also going to assume that they're near the Earth's surface, so that little g is 9.8. All right, so terminal velocity, again, when drag force equals the weight, setting those two equal and substituting in the numbers, we get 137 meters per second. Part 2, slight variation on this, find the radius of a parachute a person would need to have a safe terminal velocity. Take the safe velocity to be 8 meters per second and assume all the drag is the drag on the parachute. So we're ignoring the drag on the person now, just taking the drag on the parachute, which has a drag coefficient of 1.75. Okay, and we end up with 1.87 meters. That sounds kind of reasonable. If we got something like a 5 meter radius, that would be an indication that maybe we made a mistake somewhere, or if we got a 50 centimeter radius, maybe that's a mistake. Because if you picture how big parachutes usually are, they're often quite big. I'd say 3-4 meters across sounds reasonable. Projectile motion with drag. In 2 dimensions, we have to consider the fact that the drag force points in the direction of the in the opposite direction of the velocity. So if the object is moving with velocity v, the vector, then the drag force would be in the negative v direction. It's proportional to velocity squared, the magnitude, so the speed squared relative to the fluid. And since the unit vector in the direction of velocity is the actual velocity vector divided by the speed, then we can cross out one of the speed components. Write but don't solve the equation of motion of a cannonball fired with an initial velocity that relative to the horizontal, so 40 degrees relative to the horizontal, if the cannonball is a 10 kilogram sphere of lead, and there's the density of lead. You need the mass and the density to calculate what the volume of the sphere was, and therefore what the radius and the frontal area was for the drag equation. All right, so we set the mass times acceleration equal to the net force. Mass times acceleration is the fluid force plus the gravity force. And we can substitute in the numbers that we know. So the air density, drag coefficient, the frontal area, we can calculate what the radius is using our known mass and density, converting the density into kilograms per cubic meter, and then specifying that acceleration is the derivative of velocity and velocity is the derivative of position. The initial conditions are, it's at a initial spot, let's define that at 0, and the initial velocity was given in the problem. A little bit more information on the unit vector in the direction of velocity. V hat is this velocity unit vector. You can get it by dividing the velocity vector v by its magnitude. And here we are. If we also collect all of the constants in the drag force into one term, you can write this a little bit more simply as Fd is negative k v squared v over v. And now it's in a form you could substitute into FlexPDE. So usually you'd want to define this little v as the square root of vx squared plus vy squared. Then you can say that the x force is that set of constants times vx, and the y force is that set of constants times vy. Thank you for sticking with it so far. I hope you're not going to be disappointed by the next example, V3 rocket trajectory. So now we're going to analyze how the Soviet Union of the future fires of the alternate future from the Red Alert series would fire its ridiculous rocket on a truck. So the V3 rocket has a mass of 800 kilograms, which is 80% fuel. Drag forces on the rocket keep it facing the direction it's moving so that its thrust force is always applied in the direction of its instantaneous velocity. Imagine the rocket's firing like, and whichever way it's going, the thrust force is in that direction. The rocket expends fuel at this pretty quick rate, and the fuel leaves with a velocity of 1,000 meters a second relative to the rocket. It's a pretty powerful rocket. The rocket is fired so that it leaves the launch platform with an angle of 30 degrees and velocity 20 meters per second. So the platform is there so that the rocket can pick up some speed and leave with that velocity. If it wasn't for the launch platform, besides moving it around, the truck also angles the rocket and determines its initial trajectory. If we just tried to start firing the rocket and the truck, imagine, disappeared, then the rocket would start to tip over and fall down under gravity before it has a chance to accelerate. So we don't want that. We want it to leave with some initial velocity. What we want to do for all of this is write down the differential equation of motion for the rocket and the initial conditions, and assume that the mass given is the mass as it leaves the platform. Okay, so net force on the rocket, we've got three forces: gravity, the fluidic drag force, and the thrust force. Substituting the fact that the acceleration is the derivative of velocity, gravity points down, whereas the drag force points in the negative velocity direction, and the thrust force points in the forward velocity direction, thanks to the streamlining. We're going to substitute in our drag coefficient terms, and the thrust force from before is the fluid velocity times the fuel velocity times the rate that the fuel is leaving at least as long as we still have some fuel. So we're going to say for t is less than t thrust, and then 0 if we're past that time. And the mass just decreases proportional to the rate the fuel is leaving at. The v hat is 1 over v, vx, vy. Initial position 0 and initial velocity as given in the question. You can solve this with FlexPDE. So here's an example of that. This is the V3 rocket script. And we need to set up the variables as the velocity and the positions in x, y. Since we only need 4 variables this time, we can solve all 4 of them at once. Substitute in a lot of your definitions here in the definition section. Don't bother to pick up a calculator and then calculate what the mass as a function of time would be if you can just write it in, or say the thrust force as the product of Q and V fuel. It's faster to just kind of type them both out. Well, maybe in this case, since it's multiplying by 1,000, you could have just multiplied them by hand. But here it's a little bit more clear where all that came from. And if you want to change just one thing, say we want to say later, okay, what if we got the fuel to leave at 2,000 meters per second instead of 1,000? How would that change things? Now we can go back and edit that. So we've got our mass, the air density and all the fluid parameters collected into K, the thrust time, the initial angle, converting it to radians from degrees there, the velocity, so initial velocity, and then even though Vx and Vy are the variables we're determining from the differential equation, we can still have expressions like the velocity and then finding out maybe the total kinetic energy if we want to do that, that depend on these values that we determine from the equations. So equations, the derivative of velocity in the x direction. Remember that we have to specify the acceleration here, and so the acceleration would be the force divided by the mass. So we have to remember to divide by mass there at the end. It's thrust divided by velocity minus the fluid drag coefficient times the velocity, and then all of that times Vx divided by mass. Similarly for y, but with also a gravity term. The boundaries don't matter because we're doing a one-dimensional version of the problem, so we just have to set up some kind of a region. Now this is something you may not have seen before. We've got time 0 to t thrust, and we're going to halt if yd is less than 0. So we've got some kind of a halt condition here, which says we're going to step time 0 until the thrust time. So we're going to stop at the end of the thrust time because then the differential equations would have changed and this analysis isn't going to work after that anyway. And then if at some point along the way the height becomes negative, then we're going to stop as well. We're going to plot out what the velocities and the positions were, and also let's plot the kinetic energy just to have some fun with that, and then report on the final values at the end of this. So this report at 0, 0 is saying the 0, 0 is in terms of the position that we're at. It's going to report the final values of these, so the value at the last time step. Let's give this a shot. So there's the rocket. It goes up and then back down, and always moving forward in the x direction. It got to the user condition at the end where we had a negative height. You can see that the distance this traveled for our V3 rocket here is a little over 3 kilometers. And now one of the great benefits of putting it into a program like this is that you can say, well, how important were all of these parameters? So what if we were to change things so that, say, instead of 30 degrees, we fired it at maybe 45 degrees. Now what happens? So the rocket goes way farther. It goes 8 kilometers, but at the end of that, it's still moving up. It didn't go and smash into the ground. And in fact, the kinetic energy has started to reduce. So there's some kind of an optimum kinetic energy of the rocket, a little bit between 12 and 15 seconds. Go and have some fun, play around with this. Another thing to check with this is how important was the fluidic drag. So we can change this back to, say, 30 degrees and verify that we got back to our 3 kilometer distance. Yep, looks good. Okay, so now what we're going to try and do is see how important was the drag force. So how effective is the streamlining? What if we got rid of the streamlining by multiplying this by 20 and making the drag 20 times as strong, so we got a drag coefficient around 1, which is close to what we'd have for a non-streamlined body. Let's try this out. And we see now the rocket only went about half the distance. So streamlining really reduces the drag force. Another way to consider this is how important was the drag at this point. So suppose we take this and multiply it by 0 so that now there's no drag force. Now what happens? It goes a little bit further. It went about maybe 400 or 500 meters further at the end. So drag force is changing the final distance over the whole course of the motion by about 1/7 of what by about a seventh, factor of 1/7. This tells us a couple of things. It tells us, for one, the drag force is working in the equation. It's good to try turning off a force and seeing the effect of that, just to verify that it is making sense, that it's doing kind of what you think. And then it also gives us an idea of how effective about how strong the drag force is relative to the thrust force, how big of a deal it is to incorporate this, how much of a correction factor, because a lot of the time we'd like to do projectile problems and just ignore the drag because it makes it simpler. This gives you an idea about where that's justified and how much of a correction factor you're looking at.